And in biophysical chemistry, what we want to understand is water and also acid-base balance. So to begin with, just a quote there, things to a great extent happen as a result of what we fear the most. Know that there is no way to fail. It is the awareness in Christ Jesus that a victory given to us, like there is no way to fail for whatsoever reason. So the sooner you put that behind your brain, the better, because there's gonna be a time when you are going to be broken. But if that goes with you, it will help you. Know that we have got the same time under the sun, but procrastination will make others seem to be faster than you and yourself slower. So when you have got time to do something, do it and do it at that very moment. So let's go. We talk about the properties of water. The first thing is, what is the importance of water? Why should we talk about water? So number one, water serves as a solvent. And because it serves as a solvent, it means that majority of the reactions are going to be happening in water. That's why you need to know about water. Water is also important because it participates in many biological reactions, and it's actually the principal reactant in a lot of processes. For example, in photosynthesis, where we make glucose, which is of course important for energy. So that is the importance. Again, water determines the shape of most biomolecules, since the intra and intercellular environment for all organisms are aqueous. For example, the way a cell is going to be like this, maintained the shape because of water, because the environment inside is made up of water. And then water also stabilizes the temperature and pH of living organisms. This is important, stabilizing the temperature, because any slight change in temperature in living organisms might be able to cause death, because the enzymes in our bodies work in a strict environment. So, having understood the importance of water, we need to know the properties of water. The first property of water we need to know is its polarity. Now, water is a polar molecule. The meaning of that, it has got two ends, one that is positive and one that is negative. We don't write water like this. And the reason as to why we don't write it like that, instead we end up writing it like this, is because oxygen has got two lone pairs of electrons. And because of the lone pairs of electrons, oxygen in comparison to hydrogen is more electronegative. It pulls electrons towards itself. So because oxygen is pulling electrons away from hydrogen, even when those electrons are being shared, oxygen will end up having a partial negative charge and a partial negative charge this side, and then hydrogen will end up having partial positive charges. So the oxygen has got two partial positive charges, and it's actually the electrons, these two lone pairs. It's a pair. So oxygen has got four electrons, but they are in pairs. So two lone pairs which push these bonds away. And so this angle here, you'll find it is 104.5 because of the repulsion. In this bond, there are electrons, and then these electrons which are acting as lone pairs. So they'll be repelling each other, and so the angle is not straight. So this is known as a bend shape or a V shape. And this is important because when water is like this, you can see the hydrogen ends are going to be positive, the oxygen end is negative. That's what makes water to be a polar molecule. We call it bipolar because it has got both charges. And what is the reason for the bipolarity of water? Is because of electronegativity difference. Oxygen is more electronegative. Every molecule that has got bonds where there is an equal sharing of electrons or an even distribution of electrons, there's going to be polarity. And the reason as to why electrons are not equally shared is because there's a difference in electronegativity. So this electronegativity is going to create a permanent dipole. Look at the way the molecule is. The molecule is like this. And you can write a dipole moment for this molecule. A dipole you write an arrow going towards the most electronegative atom, and then put a line like that. And you know that from physics, when you have got a vector, you can break it in two components. So this arrow which is going in this direction, you can break it. It's going to have a forward component and an upward component like that. So that's a dipole. Same way with this arrow that is this side is going to have this. So because these two vectors are equal in magnitude but opposite in direction, they end up cancelling each other. So the net dipole of water is going to be the addition of these two. So the net dipole is going to be like this towards oxygen. This is the one that you can see. Oxygen being negative and then the other side being positive. So that's a permanent dipole that is created. And that's actually an electric pole which can determine relative solubility of molecules. So molecules that are charged, they'll be able to dissolve in water because it is also a polar molecule. Please take note, only charged molecules. Another property of water that we need to be aware of is that water forms hydrogen bonds. And this is due to the polar covalent bonds that are present in water, because water has got polar bonds. Those bonds which are polar are going to enable the water molecule to interact with other molecules. Actually, hydrogen bonds happen between hydrogen and other molecules which are electronegative. And those molecules, because hydrogen is what is in water, to be specific, is having a partial positive charge, to be able to interact with oxygen which has a negative charge, fluorine and nitrogen of other molecules, because these are going to be negatively charged. Take note that an hydrogen bond is weaker than a covalent bond, but it is longer. Okay, this bond here is covalent. It is strong, but it is it is not very long. You can see this is a hydrogen bond, is long. These hydrogen bonds are weak, but you know, even the same which says you can have fools, but if they are a lot, they are going to become strong. So hydrogen bonds, so they are weak, but because there are a lot of them, they end up becoming strong, and these are the ones that hold water. That's why you can't have one water at a given time. They always move together because of a lot of hydrogen bonds. Each water molecule, is important for you to know that it forms four other bonds with it will form four bonds with four other water molecules. That is very important. These are hydrogen bonds that it forms, four of them. Actually, to be specific, I'm going to tell you that ice water is the one that will form these four bonds. For liquid water, it is going to form, we will say it has got an average, like let's say 3.4 or 3.6 bonds. That's an average, because in liquid water, bonds are constantly making and breaking, because liquid water flows. Because of the ability to flow, bonds are constantly breaking and making, and so you can't really say, okay, there are four bonds at this point. Hope you get that. As I said earlier, the length of the bond is about twice the covalent. The length of a hydrogen bond is twice that of a covalent bond. And these bonds are weaker than covalent bonds, as we said earlier. Another property you need to know is that water has got high melting point. And this high melting point, actually the properties of water is because of its bipolar nature, because of the hydrogen bonds. So high melting point is because of the hydrogen bonds. And what's the importance of it? So for you to melt water, melting is changing something from, is from solid to liquid. So you need a lot of heat for you to be able to convert a liquid from a solid water, which is ice, into liquid water. It's also important to know that the density of water decreases as it cools. And this is known as the anomalous expansion of water, or the anomalous property of water. Normally, what should happen is that as you get to increase the temperature of something, its volume expands. But for water, when you talk about volume, what will be happening as you increase the temperature, the volume is increasing, but you reach to a certain point where the volume will no longer increase. So there is actually a maximum point. So in other words, for water, whether you are reducing the temperature or increasing the temperature, the volume can still increase. That's why if you put a bottle full of water in a fridge, you can find that it has broken, because whether you are cooling water or heating water, it can still increase. About density, again, you need to know that dense water is densest at 4 degrees Celsius. What happens that below 4 degrees, there is no much, the density is not very high. This is density this side. And then above this side, so this is 4 degrees, highest density. Above and below, the density of water is low. This property is going to be important because, so that tells you that between, let's say you're talking about water that is at 0 degrees, at 1 degrees, 1 degree, 3 and 4. It means that the one that is at 1 is more, a bit of warm in comparison to 0. And you know, if water is at 0, it means that it is ice. So ice is going to be on top when it comes in cold season. You find that for a river or ocean, you are going to see ice on top, very cold water. But at the bottom, as you go down, water is going to be becoming warmer. That is why you can't fish in cold season. Why? Because fish is going to be at the bottom. That's where water is hot or warm, to say. So the property is very important there. Another thing that you need to know about density is that for water, normally you learned in high school that if you have got a solid and a solid particles are closely packed, and then liquids, they are sparsely packed. This is going to be opposite for water. Liquid water, the particles are closely packed, while solid water, which is ice, the particles are sparsely packed. And this tells you why. Because solid water, the particles are sparsely packed, it can float on top of liquid water because it doesn't have a higher density. Because normally liquids are supposed to be low denser than the solid counterpart. Okay, so make sure that you take note of that. And so we have already said that ice is going to be able to form a lattice, is forming like a platter on top of the liquid water. Please be free to ask any question in case you have got one. Water also has, I've talked about the property for density and the application for fish, right? Aqueous environment. The aqueous, the fish is going to go at the bottom because it is warmer there. And then water has got a high specific heat capacity. Specific heat capacity is the amount of heat energy that you have to give to a compound to change it, okay, to change the temperature, to raise the temperature by only 1 degree Celsius. Say if water is at 24 degrees Celsius, you want to go to 25 degrees Celsius, we are raising it by 1 degree Celsius. That is known as heat capacity. But if I put the word specific, it means that I'm talking about 1 gram. So specific heat capacity is the amount of heat energy that you need to give 1 gram of water to raise the temperature by 1 degree Celsius. Now, the meaning of this is, what's the importance of that? Water has got a high specific heat capacity. The meaning is that for it just to change the temperature of water from by 1 degree Celsius, you need a lot and a lot of heat. And this is going to be important, say, for chemical reactions, okay, in our bodies. Because chemical reactions have got the optimum temperature. So you don't want the temperature to easily change. Because if the temperature easily changes, it means that you are going to affect the enzymes. So the specific heat capacity of water is important in that it is going to maintain a constant internal environment, and that is known as homeostasis. Because any slight change in temperature is going to kill our enzymes. Okay. Another important thing we need to know, so this high specific heat capacity is actually because this is due to the fact that hydrogen bonds must be broken to increase the kinetic energy. For you to break those hydrogen bonds, you need a lot of heat for you to be able to increase the kinetic energy so that the bonds can start separating. Another property is that water has got a high heat of vaporization. Vaporization is the heat that you need for you to convert water from liquid into a gas. Now, this is not when you are heating, okay? If you are heating, that is known as boiling, but this is vaporization just at room temperature. Now, at room temperature, it is very hard for you to convert liquid water to gas. So you need a lot of heat, and the same thing, you need a lot of heat to break the hydrogen bonds. The importance of this is that by the time you're converting liquid water to gas, you would have lost a lot of heat because you can't convert liquid water to gas unless you take in a lot of heat. This is important in cooling. The cooling effect, say in hot seasons, and for dogs when they are panting, right? They'll be losing water like that, and that will help them to cool. That's the importance of heat of vaporization. Water is a universal property, and that's because it is bipolar, it is charged, and it interacts with compounds that are charged. So charged compounds, we call them hydrophilic because they love water. So what happens is that those compounds that are charged, like for example, we'll talk about this in organic chemistry as a mechanism. When you have got sodium, sodium is going to be surrounded by the positive ends of water, and you know the positive ends of water are the oxygens, like that. And where a charged molecule is surrounded by another molecule, that is known as solvation. So for example, the salt that we use, sodium chloride, undergoes what we call solvolysis. Solvolysis is being broken by being surrounded. So the sodium is going to be surrounded by water, specifically the oxygen part of the water, while the chlorine is going to be surrounded also, but specifically by the hydrogen part of the water, because that's the part that is positive, because the positive is supposed to interact with the negative. Because these two guys have been kept away from each other, that is, they've been broken. That's solvolysis. So the solubility of organic compounds actually depends on the polarity and the ability to form hydrogen bonds. So organic compounds, majority of them, actually alkanes, alkenes, and alkenes, are mostly going to be non insoluble in water because they contain a lot of carbon hydrogen bonds, and these bonds are non-polar. So any molecule that is non-polar can't dissolve in water. Again, this is what I was just explaining. You can see the way the charges have been surrounded, those which are negative and those that are positive. So you have got some functional groups that can dissolve in water because they are charged, like carboxylates. These guys are like these. Okay, you have got carbon double bonded to oxygen. That's a bond between carbon and oxygen is a charged bond. And then amine is it. So this is a bond between a nitrogen and hydrogen. This is also a polar bonds. Amino group. Like you know the way amino acids are, like the NH2. So these are also hydroxyls and carbonyl. Carbonyl is a carbon like this. So you need to differentiate carboxylate and carbonyl. Carbonyl is like this. It will actually be bonded to a hydrogen also because each carbon is supposed to have four bonds. And then you are going to have another group this side. This is a carbonyl. This is a group that you find in carbohydrates. And then carboxylates or carboxylic acid functional group, you have got a carbon double bonded to oxygen, but you have got OH. And then you can have another molecule. So those are the two. So these molecules are all having an oxygen, hydrogen, and nitrogen bonded to these other lead to electronegative atoms, and so the bonds end up being polar, and so they can dissolve in water. As the number of polar groups increases in a molecule, the solubility of that molecule is going to increase because there will be more interaction with water by forming hydrogen bonds. Hydrophobic interactions are interactions that can happen with non-charged molecules or molecules that are not polar. For example, the organic compounds that have got a lot of carbons and hydrogens. Say, for example, you have got a compound that has got these bonds. A lot of them, we can put N there, maybe N is 20. So these guys will be able to interact with themselves. Remember, like dissolves like. So if I'm non-polar, I am going to interact with what is non-polar. That's why you can see these two non-polar guys, they ended up interacting. So non-polar molecules are actually going to be excluded and associate with each other. That is known as hydrophobic effect. And the associated interaction is called the hydrophobic interaction. That is why when you look at the structure of the cell membrane, we'll talk about this in physiology. The structure of the cell membrane, it is bipolar. So you have got the head, because it's made up of phospholipid. The phospholipid has got the head, which is polar because it's a phosphate, and then the tail is non-polar. So you are going to see the way the molecule is going to be arranged like this. So you can see the tails, which are non-polar, they are interacting with themselves, while the heads, which are polar, are interacting with these surfaces. This can be the inside of the cell, and then this can be the outside of the cell, because both the inside of the cell and the outside of the cell has got water. And then on the middle here, that's where the tails are interacting, because they don't want to interact with water. Instead, they want to interact with themselves because they are non-polar. Those are hydrophobic interactions. Okay, so you can see this is a phospholipid example that we can have. And because of this hydrophobicity, these molecules, which are non-charged, they can form what we call micelles. Micelles, this is, for example, you have got a phospholipid here, a phosphate head which is charged, and then you have got a fatty acid down here that is not charged. The fatty acids will end up interacting with themselves, and then the heads which are charged will be outside, so that they can interact with the water molecules which are charged, and that's known as a micelle. Molecules, for example, detergents, these soaps that we use, they are supposed to have a part that interacts. You know when you are washing, right? When you are washing clothes, you are putting in water that is polar. But at the same time, let's say, for example, you were eating meat, and let's say the fat of the meat fell on your clothes you are washing. So the soap that you are using should be able to interact with the fat on your shirt, at the same time should be able to interact with the water. So detergents or surfactants therefore are going to be amphipathic. They have got both hydrophilic ends and hydrophobic ends. The ends that love water and the ends that hate water. Usually they have got hydrophobic chain of 12 carbon atoms plus an ionic or polar end. So we're going to have 12 carbons, a lot of them, and then only the head is going to be polar, meaning the tail is non-polar. Soaps are alkaline metals, and these salts, they actually have got, soaps, they've got a long chain fatty acid. For example, sodium palmitate, we'll discuss this in biochemistry, of course, when we start talking about the lipids. And you have got synthetic detergents. All these, they're actually both non-polar and polar, hydrophobic and hydrophilic. That's amphipathic. So all of these soaps that we've talked about, or detergents or amphipathic molecules, they will be able to form micelles, which are a sphere in which hydrophilic heads are outside interacting with water, and the hydrophobic tails are inwards. And this is used to trap greasy and oils inside to remove them. So oily things will be here to interact with the lipid component, so that they can be removed when you are washing. Water has got can undergo different types of interactions, and not only water, other molecules of life. Molecules of life, we call them biomolecules. Bio means life. So other biomolecules can have different interactions, and there are four main interactions. The first ones are the hydrogen bonds. Nearly all the biomolecules will undergo these interactions. But what are the examples of biomolecules? You have got the lipids, the proteins, the carbohydrates, the nucleic acids, the enzymes. All these are biomolecules. They'll undergo these, they can form these interactions of bonds. Hydrophobic hydrogen bonds, they are more important between and within molecules. They'll be able to stabilize the structures of proteins and nucleic acids, because these guys are polar. Not lipids mostly, because lipids are non-polar, they will not form hydrogen bonds. Hydrophobic interactions, these ones are weak interactions, and they are important in protein shape, just in the shape, okay, and also in the membrane, because you have got, of course, in the membrane you have got lipids there, like the phospholipids. You also have the charge to charge interactions, or the electrostatic interactions, like the ionic bonds, which occur between two oppositely charged particles. The strongest non-covalent forces are actually these ionic bonds. When you look at the strength of bonds, covalent bonds are the strongest, followed by the ionic bonds, and then you're going to have these are hydrogen bonds, and then you're going to have the van der Waals forces. So these ionic bonds can be weakened significantly by water molecules. The reason for that is when you have got sodium here and chlorine here, and then you put this in water. This is supposed to be sodium chloride. Water is going to come and surround this chlorine and then surround this sodium, and so they will be able to be weakened in water. And then van der Waals forces. Van der Waals forces, they are also known as the London dispersion forces. These forces occur in every molecule, whether charged or non-charged. For example, here is a molecule and here is another molecule. These guys have got electrons. And what happens is that because electrons are both negatively charged, there's going to be repulsion when you bring these molecules together. So these electrons will be pushed aside, these electrons will be pushed aside. So what you are going to see that electrons are going to concentrate on one end, and the end where the electrons have concentrated, they will be partially negative because electrons are negative. The end that has got few electrons will be partially positive. And so you have got these transient charges that have been formed. Okay, there's a transient dipole which has been generated, and that is what we call a van der Waals force. And because of this, this molecule can now interact with other molecules like that, but these are very weak bonds. Nucleophilic nature of water. So water acts as a nucleophile. We'll discuss nucleophilic and electrophilic reactions in the organic chemistry. But a nucleophile is a molecule that loves the nucleus. Look at the way water is. Water is like this, and it has got lone pairs of electrons. So what water is going to be doing is that when it sees because it has got electrons are negative, right? And they are found in a shell. What is found in the nucleus are protons, and they are positive. So these negative things will be attracted to the protons which are found in the nucleus. So something that loves the nucleus is known as a nucleophile. Phile means to love. And something that loves electrons is known as an electrophile. So nucleophiles are compounds that are negatively charged, or they have got lone pairs of electrons. Electrophiles will be molecules, let's say for example, something that is positively charged. Let's say for example, I can say NH4 positive. Say this one, it's positively charged. So what will happen is that this can go and attack the nitrogen. Why? Because it has got electrons, so it loves the nucleus, so it is the nucleophile. And then this molecule, because it is positively charged, it loves what is negative, so it is an electrophile. So nucleophiles attack electrophiles. More we understand in organic chemistry. So examples of nucleophiles, you have got oxygen, nitrogen, sulfur, carbon, even water. Basically, most of the molecules that are going to have a negative charge or a lone pair of electron. And this is going to be important in condensation reactions where hydrolysis reactions are favored. For example, proteins can be broken down to amino acids because of this nucleophilicity of the water molecules. Actually, you know that when you are forming disaccharides or polysaccharides, such a reaction is a condensation reaction. You lose water. And that's because there is actually an attack that is happening. So let me give you just a simple mechanism so that you understand how these reactions happen. Say this is water. It has got two lone pairs of electrons. And say you want it to react with hydrochloric acid. You can see the way hydrochloric acid is. So for hydrochloric acid, hydrogen is the one that is going to be positive. Chlorine is going to be negative because chlorine is more electronegative. So what happens that the oxygen here is going to attack this hydrogen. When it attacks this hydrogen, this bond is going to break. And this is how you are going to be showing reactions if they ask you to write a mechanism. in organic chemistry. And so that bond breaks, and so you're going to have now oxygen being like that, and then it's bonded to hydrogen, and it's going to be positively charged because now it has got three bonds. Then the chlorine is going to be alone. So this is just an example of how nucleophilic reactions happen. Water can also undergo ionization. So pure water ionizes slightly. So to ionize is basically to break when you dissolve something in water. Water can actually dissolve in itself. Okay, that's known as auto-ionization of water. So you can see water can actually break and it will form hydrogen ion and hydroxide ion. This is a proton. And so water can act as both a base and an acid. A base is a proton acceptor, and acid is a proton donor. So if I'm reacting water with hydrochloric acid, in this case, because I already have an acid, water is going to be acting as a base. So it will be accepting a proton. So the hydrogen is going to be gotten. I already showed you how the mechanism happens. So we're going to form H3O plus and then plus chloride. But when water is reacting with a base, for example, sodium hydroxide, is going to act as a proton donor. And so what you are going to end up forming is you are going to end up forming water, and you are going to form hydroxide. Actually, forget about this sodium here. It's more like just keeping the charge. So one hydrogen is going to move from this water. It will go to this OH, and that will form water. And then this, which was the water, will remain as OH. That's the one that forms there. So that's the reaction. You can see water acting as both an acid and a base. So when you have got two water molecules, as we have already said, what will happen is that one of the water molecules will donate an hydrogen to another. It ends up being H3O plus, and then the other will remain as OH. But again, you can just have one water molecule breaking to form H and OH. That tells you that the concentration of hydronium H3O plus, this one, hydronium, and the concentration of hydrogen is the same. Therefore, let's say I want to calculate pH. If I want to calculate the pH, I can either say pH is given by negative log of the concentration of hydrogen, or I can use the concentration of hydronium, because the concentration of these two guys is the same. The actual probability of hydrogen atom in pure water existing as hydrogen ion is approximately 1.8 times 10 to the power negative 9. Not for you to master, of course. So you can calculate the equilibrium constant of water, because the way water is, look at this, H2O, and then it can undergo hydrolysis to form H plus and then plus hydroxide. This is a liquid. This is going to be in aqueous. It's dissolved when this is in aqueous. And you know the way we calculate equilibrium constant K is given by the concentration of the product. So I've got H plus and then times the concentration of the other one. If there were numbers in front, those become powers. For example, if there was a 2 here, to become power 2. You're supposed to divide it by the concentration of the reactant. But remember, when you're using K, you only include gases and those things which are in aqueous. You don't include solids and liquids. So instead of me saying over water, I'll not include this water. Okay? So that gives us what we call the dissociation constant for water, and that is known as Kw. So Kw is given by the concentration of hydrogen multiplied by the concentration of hydroxide, the water dissociation constant. And for pure water, the concentration of hydrogen and the concentration of hydroxide is normally the same for pure water. Since Kw is going to be equal to 1 times 10 to the power negative 14, okay, which we can see, where is it here? It's this one here. That will mean that the concentration of hydrogen alone is 1 times 10 to the power negative 7, and also the hydroxide is that same one. So because you can calculate, so since we know the Kw, we can say concentration of hydrogen times concentration of hydroxide is equal to Kw. And so we'll say concentration of hydrogen and hydroxide is the same. So that will be where there is concentration, I'll put X. So that will be x squared is equal to 1 times 10 to the power negative 14. And then I can now square root both sides. That will give us 1 times 10 to the power negative 7. That's a concentration of hydrogen. Therefore, if I want to find the pH of pure water, it's going to be negative log of the concentration of hydrogen, which is 1 times 10 to the power negative 7. And this is actually a 7. So that is the pH of pure water. So we've already mentioned that. Now another thing you need to know, I talked about pH here. Why? We say pH because we are using the negative log of the concentration of He. But you can also find what we call POH when we are using the negative log of the concentration of OH. In other words, P of something, P of X is always negative log of that same X. So if I'm talking about P of OH, POH is going to be negative log of OH. I only talked about pH. I can also calculate POH and it will still give me 7 because the concentration of hydrogen and hydroxide was the same. Therefore, I can get pH and add with POH. 7 plus 7, that will give me 14. And that is known as pKw. You can also say pKw. How can I find pKw? Simply negative log of kW. Remember, P of anything is just negative log of that same thing. And remember, I said that kW is 1 times 10 to the power negative 14. Therefore, negative log of 1 times 10 to the power negative 14 will give you 14. So 7 plus 7 is equal to 14. Okay, so something like that. If the pH is less than 7, you know that is acidic. If it's greater than 7, that is basic or alkaline. So that gives us a good introduction to what we call acid and bases. When a compound, when you get a compound and then it loses an hydrogen, for example, you have got sodium. When sodium loses, and let's say it loses electrons, it will become sodium ion. Because it has become charged by losing, or oxygen, when it gains electrons, it will become oxygen ion. Because it has become an ion by gaining electrons, that's known as ionization. But when a compound becomes an ion by being broken in water, by dissolving in water, that's known as dissociation. For example, sodium chloride, when you dissolve in water, it's going to dissociate into sodium and chloride. You formed ions. That's dissociation. Ionization is losing or gaining. Dissociation is forming an ion by dissolving in water. Weak acids, these are, so when you're talking about acids, you can have weak or strong, and concentrated or non-concentrated. When you're talking about concentration, you're talking about how many hydrogen ions you have in solution in water. How many are they? But when you're talking about weak and strong, you're talking about the ability to disassociate. So molecules that strongly disassociate in water, you say they are strong acids. Okay, they completely disassociate. And then molecules that only partially disassociate in water, they are weak acids. So weak acids will show them like this. When they are disassociating, we'll write a forward arrow and a backward arrow. So we're going to have H minus and then H plus. But for strong ones, strong acids like hydrochloric acid, you just write one arrow because it completely disassociates in water. Okay. So these weak acids and the weak bases, they are common in biological systems and they are going to play an important role in metabolism and regulation. Acids may be defined as any proton donor and bases proton acceptors. So the weak acids and bases, they actually form buffers, and those buffers are what are important. Now the importance of a weak acid and a weak base, not just weak acid and weak base, is acid and base is that when you have got an acid is like this HX. When an acid loses an hydrogen, it becomes X minus. So this guy and this guy, they are known as conjugates of each other. The way you are going to tell conjugates of each other is that they are only different by one hydrogen. For example, I can have H3PO4 and H2PO4 minus. These are conjugates. Not this one with HPO42 minus. These are not conjugates because they differ by two hydrogens. So conjugates of each other, they differ by one hydrogen, and the one that has got more hydrogens is always the acid. For example, you can see here acetic acid, which has been shown, it has lost an hydrogen. So you have got acetic acid and acetate ion. These are conjugates of each other. Each acid has a characteristic tendency to lose its proton in aqueous solution. And the stronger the acid, the greater its tendency to lose the proton. That is going to be important in organic chemistry. How easily something loses an hydrogen means it is how strong it is. Those that can't easily lose an hydrogen, they are not strong. Just like when you are in a heartbreak, you can't easily let go. It means you are weak. But if you can easily let go, you are strong. Hope you get that. Yes, please. Is there a question? Is there a question? Okay. So when you're talking about the strength of an acid, you can use what we call the pKa. pKa of an acid is the pH at which the acid is half disassociated. So you know an acid is in the form Ha, right? And then it will be converted into hydrogen ion and A minus. So at a point where it is only half disassociated, meaning that you have got equal amount of this and this. Let's say, for example, you started with 100 of this and then you didn't have any product, but now you have got 50, 50. So at that point where the concentration of these two guys are the same, the pH at that point is what we call the pKa. Okay. So the stronger the acid, the lower its pKa. Now, when you're talking about this association of an acid or a base, you can use what we call the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation describes the dissociation of a weak acid in the presence of its conjugate base. So if you have got this as an acid, you can see it is dissociating into H plus and A minus. And then you can find the equilibrium constant. So please take note that okay, let me describe this. Take note that Ka is the dissociation constant of an acid. So when you have got a monoprotic acid, an acid that has got only one proton, like this, and it's a weak acid, when it disassociates, you are going from H plus and then plus A minus. You can find the acid dissociation constant, which is a Ka, just like we talked about Kw. K is always found by the concentration on the product, that's hydrogen, multiplied by A minus, and then divided by the concentration on the reactant. But because for this one, this is going to be also dissolved in water, so we can also include it Ha. Okay, like that. And then Ka tells you of how easily something disassociates. So the higher the Ka, high Ka corresponds to low pK. Let me first derive the equation, the Anderson-Hasselbalch equation. So the Ka is equal to H plus A minus over Ha. So what we can again do is we can say Ka is equal to, I'm going to put H alone like this, and then I'm going to put A minus, and then Ha. And then I'm going to introduce negative log both sides of the equation. Negative log of Ka is equal to introduce also negative log this side of H, and then A minus over Ha. And then negative log of Ka, remember we said negative log of anything is just P of that same thing. So negative log of Ka is P Ka. And for this negative log of H and then this part, we are going to split it. Okay, we'll split it. You know from the rules of logarithms, when you have got log of AB, this is actually log of A plus log of B. So because there's a minus in front here, so it's going to be negative log of H and then minus log of A minus divided by HA. And then I can take it on top. We'll say pKa is equal to negative log of H, that is pH. That will be minus log of A minus divided by HA. So this is what we call the Anderson-Hasselbalch equation. Okay, that's the Anderson-Hasselbalch equation. But we can rearrange this equation instead of ending here so that we can make pH the subject of the formula. So we'll say pH is equal to pKa, and then I'll take this term the other side so it will become positive log of A minus divided by HA. So this is actually the one that we use. And the A, so you see we've written like this, pH is equal to pKa. Remember I told you that when you have got conjugates of each other, the one that doesn't has a hydrogen is always the base. So pH is equal to pKa plus log of the base, that's a conjugate base, over the acid. So that is the equation there, Anderson-Hasselbalch equation. So you can have an example here. What is the pH of a solution of 0.1 molar acetic acid and 0.2 molar acetate ion? So the acetate ion here, acetic acid, that is CH3, COOH. This is going to disassociate like that. Then we're going to have CH3, COO minus, hydrogen has been lost like this. And so for what you're going to see is that this is a base. And we've been told that the pH, sorry, the concentration for this base, acetate ion, given, so what is the pH of a solution of 0.1 molar acetic acid? So acetic acid is 0.1 molar and 0.2 molar acetate ion, 0.2 molar there. So using the equation, pH is equal to pKa, and they've given us the pKa there. If they've given you Ka, you find the negative log of Ka to find the pKa. That will be 4.8, and then plus log concentration of the base. The base here is 0.2, the acid is 0.1. If you punch that in the calculator, that will give you 5.1. So you can also have another example. What is the pH of a solution whose hydroxide concentration is this? Now they've given you the hydroxide concentration, OH. So you can find what we call the POH phase, which is given by negative log of OH. And that will give you 3.4. And when you know the POH, when you add pH and POH, you are supposed to get pKw, which is 14. So therefore pH is 14 minus POH, and that will give you 10.6. The last concept you need to understand when it comes to this topic are buffers. A buffer is a solution which is made up of a weak acid and their bases, which resist a change in pH. And the aim is you want to maintain a constant internal environment. Buffers are aqueous systems that tend to resist change in pH. Please take note that when a small amount, not large, small amount of acid or base is added, because for example, you have got CH3COOH. This is the acid. The conjugate is going to be CH3COO minus. This is the conjugate base. So this guy has got the acid part and the base part. So what happens is when I add an acid, it will come and react with the base. When I add the base, it will come and react with the acid. And so we'll be maintaining a constant pH. Okay. And take note that you form buffers by using a weak acid or a weak base with its conjugate, not strong. What's the importance of buffers? Most of the enzymes work at an optimum pH, so you don't want the temperature to be the pH to be changing very much. So that's why you need to make sure that the pH is maintained constant. Both the inside of the cell and the outside of the cell, the fluids there have got a lot of organisms and they require a constant pH. Therefore, buffers are there to help in maintaining that constant pH. Buffers will actually act as a first line of defense. They are part of the immune system. And the first line of defense, we call it the innate immune system. We understand that in immunology. The innate immune system helps us in fighting infection that has come in our body for the first time before the specific part of the immune system that is just targeted to that microorganism that is entered the body can come in. So this is the first line of defense. Okay. Biological buffers will include the you are going to have the bicarbonate, the phosphate, and the proteins. These are the main buffers. Proteins contain amino acids, and the amino acids they are functional groups. So an amino acid is in this form. It has got H, R, and then it has got a carbon bonded to H and then OH, and then it has got a nitrogen which is bonded to hydrogen like this. So these functional groups, this one and this one, for proteins, these are the ones that will be acting as buffers. Phosphate group of nucleotides function as weak buffers. Also, nucleotides like the adenines, actually nucleotides like the DNA and the RNA. These guys have got these phosphates. If you remember from first year, we talked about the phosphodiester bonds. So those phosphates actually help in acting as a buffer. So the phosphate buffer, this buffer is found inside the cell. Take note of that, is intracellular in the cytoplasm of all cells. And for a phosphate buffer, remember the way phosphate is, it's like phosphoric acid is like this. If this guy disassociates, it's going to form H2, is losing one hydrogen, PO4. When something loses hydrogen, it becomes negative. Again, when this one loses another hydrogen, it becomes HPO4, now with a 2 minus. So it is these two guys which act as the buffers. They are conjugates of each other. You can see they have got a difference of one hydrogen. The one with a lot of hydrogens is the acid. The one with fewer hydrogens is the base. So you have got the acid that is conjugate base. So this guy here, because you want to maintain the its charge, right? You don't want that negative sign to be there. So you'll be able to react them with group 1 elements, for example, sodium. So we're going to see it written like that because it has got only one negative charge. Sodium is positive, so we'll include sodium there, and then we'll put now the H2PO4. So this is sodium dihydrogen phosphate. And then for this one, which is the base, because it has got two negative charges, we use two sodiums like this. So this is disodium hydrogen phosphate. So disodium hydrogen phosphate is the base, while sodium dihydrogen phosphate is the acid. Phosphate buffer system will work effectively at a close pH, a pH, trying to maintain a pH close to 6.86. Okay, so it will be resisting changes in pH from 5.9 to 7.9. Not that we should really master that. And then the bicarbonate buffer system. Bicarbonate buffer system, this one is to do with carbonic acid. Carbonic acid is like this. This can disassociate, you lose one hydrogen, and then you remain with a bicarbonate, which is like this. So it is this guy and this guy which forms a buffer. And this buffer, the blood plasma is in part buffered by this system. This buffer is more complex than other conjugate acid base pairs. One of the components, the carbonic acid, is formed when carbon dioxide reacts with water. So you see the way this carbonic acid is. What happens that when you have a lot of carbon dioxide in the body, it can react with water. Using the enzyme which is known as carbonic anhydrase, you are going to now form that. Same carbonic anhydrase can also do the same in the opposite direction. And then the bicarbonate can also disassociate like that. Carbon dioxide is released from the respiratory system. That's why this buffer system is related to the respiratory system because of the carbon dioxide. The pH of a bicarbonate buffer system depends on the concentration of the carbonic acid and H, and the bicarbonate is supposed to be HCO3 minus. Okay. And the concentration of the bicarbonate carbonic acid depends on the concentration of dissolved carbon dioxide. Remember, when you have got a lot of carbon dioxide, it will react with water to form more carbonic acid. So its concentration depends on that. And I've already talked about what is happening here. The carbonic acid can be produced by the reaction of carbon dioxide with water. And then it can now break down into hydrogen and bicarbonate. At the same time, when the carbonic acid breaks into carbon dioxide and water, the carbon dioxide that is released, it can go to the lungs and then removed from the respiratory system by breathing. That's why there is a relationship. Okay. So there is the aqueous phase in blood where you have got this buffer system acting, and then you have got the gas phase where you've got the carbon dioxide going to the lungs to be removed. Our pH in the body, the pH is actually between 7.35 to 7.45. So you can take an average of 7.4. That's our blood pH. So you want to make sure that you maintain this pH, because if pH increases, it can become deadly, lethal, and it can also disturb the enzymes because they work at strictly regulated pHs. So because of this, because of the relationship with the respiratory system, we can talk about acid base disturbances, some clinical application. So in respiratory, alkalosis. Alkalosis is where you have got a high pH. So remember this, carbon dioxide is removed where? From the respiratory system. So what happens is this. When you have got carbon dioxide in your body, let's say you start breathing fast, right? So what happens is that you are removing a lot of carbon dioxide. And remember, we said that carbon dioxide can react with water to form at the end of it all. So it can react with water. And then you are going to form what? Carbonic acid. This carbonic acid can form what? Hydrogen and bicarbonate. But for this, I'm interested in the hydrogen ion. If I'm breathing very fast, I'm losing a lot of carbon dioxide, and so the carbon dioxide has reduced, isn't it? The carbon dioxide has reduced. And when the carbon dioxide reduces, it means that I'm going to have a reduction in hydrogen also. A reduction in hydrogen causes what? Alkalosis. So hyperventilation is going to be able to cause alkalosis. Maybe if you are anxious, you start breathing out very fast, and that can result in respiratory alkalosis. Respiratory alkalosis can also be caused by you taking some drugs like salicylates. An example of such a drug is aspirin. When you take aspirin, you can also have respiratory alkalosis, fever, artificial ventilation where you are breathing using some other methods, or even high altitude when you go very much high. The condition is not too good, it can be deadly. All right. But if I'm not breathing out carbon dioxide very much, let's say for example, there is a blockade in my respiratory system. Maybe there's something in my airways. I can't remove carbon dioxide. So carbon dioxide will end up accumulating. And so there will be high levels of hydrogen. So hypoventilation leads to respiratory acidosis because a lot of hydrogen causes what? High pH. Okay. So this happens in conditions where the respiratory system is blocked, where the respiratory system is blocked or it is constricting, like there is compression here. That's known as bronchoconstriction. Example of such conditions are obstructive lung diseases, for example, asthma, you have got emphysema, chronic bronchitis. So those conditions, there is airway obstruction. So those are the main ones that we can understand. This is acidosis and alkalosis when it comes to the respiratory system. But acidosis and alkalosis can also be caused by the production of the acid and base, and not the failure to remove carbon dioxide or removing a lot. Let's say, for example, if the body is just producing a lot of acids, there is overproduction, okay, increased production of acid by the body. That is going to result in metabolic acidosis. Not that the body is failing to remove carbon dioxide, no, there is production. For example, if you are fasting, what happens is that the body will start breaking down lipids. And when you break down lipids, you are breaking them so that you can use them for energy. That is known as beta oxidation. We'll talk about that later on in biochemistry. And as you are doing that, you are releasing a lot of hydrogen ions, and that causes what we call lactic acidosis because you are going to be producing lactate. Actually, when you are breaking down lipids, you'll be forming what we call you are going to be forming this acetic acid, beta hydrobutyric acid, and acetone. So these products, when you are, let's say you are fasting, or someone that has got diabetes, like acetone itself, it gives a bad smell. So someone that has got diabetes, you can actually use that smell to be able to confirm when they are producing these. We call these as ketone bodies, the acetoacetate and hydroxybutyric acid, and also acetone. These are not the only ones that can cause metabolic acidosis when they are produced. Also, ingestion of aspirin, just like it was also causing the other one. And also ethylene glycol, when you ingest this, or methyl alcohol. These alcohols are also acidic. Some, they have got some acidity, so they can cause metabolic acidosis. So metabolic acidosis is not about the respiratory system. It's where you are either taking in a lot of acid, or you are producing a lot of acid. While metabolic alkalosis is you are removing too much acid, okay, or you are taking in a lot of base. For example, actually, alkaline materials cannot be synthesized from neutral starting materials. So metabolic alkalosis is not going to be caused by production of base, but instead by excess intake of the base, or by abnormal loss of acid. For example, if you are vomiting. So if someone is vomiting, the stomach is near to the mouth. When you are vomiting, you'll be losing acid. So you are going to have alkalosis, specifically metabolic alkalosis. But when you have got diarrhea, you are going to be losing more of the base. So you are going to end up with a lot of acid. So diarrhea causes acidosis, while vomiting causes alkalosis. So take note of that. So as a summary, when it comes to the buffers found outside the cell, you have got the bicarbonate buffer. That's a major one. In blood, you have got the bicarbonate buffer and hemoglobin. While inside the cells, you have got the protein buffer as the major one. So take note of that. So for exam questions, you can try out these questions. We'll see if you can be able to answer what we've discussed. If you answer, you can simply react by posting in the comment section. If there are some questions that you have failed to answer, make sure that you get also to get in touch. In case you have answered and you want to confirm your answers, you can send your answers on WhatsApp to 097401 62 68. And here we end for now. Thank you so much for being present.